One, two, three. Okay, I think now you can hear me. Well, oh, sorry guys about the. Yeah, we normally have a lot of problems at the very beginning of the. Okay, thank you guys. Thank you for your feedback. But don't mind, you can turn on your mic because yeah, midway through coding, uh I might be confused to go into the chats and actually read what you are texting me. So feel free to turn on your mic and talk to me whenever it is needed. So sorry, I spoke a lot and you didn't hear me. So basically, I introduced myself and I said we had a training last week about C++, and now we go through that very fast. Just to review what we did last week. We have another chat. Let me see what. Okay, thank you. Okay, yeah, like I said, my name is Ali. The focus of my work at the moment, I'm a researcher at University College Dublin, and the focus of my work is the simulation of severe deformation. I have a bit of experience in OpenFOAM, and I am the CTO of TensorFields, which is an initiative of OpenFOAM training and OpenFOAM consultation services. These are a few images about what I am specifically working on. And yeah, I introduced TensorFields also. The goal of our training is obviously writing the engineering standard C++ computational tools. Obviously, in 2 hours, you do not get to an industry level, but we think our approach is unique in the sense that we start from scratch and we make our attendees ready to start their journey. So what we will do today, what we did actually last week in the previous session was writing an application and a library in C++. And today we will actually use that skill and knowledge to solve a real partial differential equation using OpenFOAM core libraries, which enables us to do so. Actually, I might skip a few slides that we had last week. We reviewed C++, what C++ is and what object-oriented programming is last week. A few review on actually C++ technicalities also. And finally, we ended up with some actually, yeah, some simple C++ applications and library implementations. Now, today we are gonna actually implement a working solver. So what you're looking at is, let's say you are going to solve the steady state heat conduction equation. Well, as far as I see, oh, excuse me, you do not see my screen. I just noticed. So let me share my whole screen, basically. Share. Okay, thankfully you see that now. Uh, so if you are going to solve a steady state heat conduction equation, what happens is that at the first place, you discretize your domain into cells, then you integrate your equation over every single cell, and then after some mathematical manipulation using the divergence theorem and mean value integral theorem, you end up with an algebraic equation which is equivalent to your integral. And when you do this integration process for every single cell, you will end up with, actually, this is the final equation for one cell. And when you do this for all the cells, you end up with a system of equations. Each row is an equation for one cell. So the process basically is, at the first place, we need to discretize our domain then. Let's create actually a text file which does that for us. I maybe need to increase my font a bit, and go to the proper directory. I will create a directory called, so here I have no fluff. I go to no fluff. I create draft is our program today. I go to draft. So what I'm going to do now is I will create a text file called, so first of all, let me create a directory. By the way, this is the process for solving basically a PDE. I gave an example of a heat equation, but we are going to solve wave equation as wave equation solver. The way we implement it does not exist in the standard OpenFOAM forks. So it gives us a bit of taste as to how to implement a new solver. So I make a directory called wavefoam. I go into it and I create wavefoam.c. Last week we said that C++ codes can have a number of suffixes, including capital C. And again, we said that every C++ application has a main function. So now let's write the plan of our PDE, solving a PDE. Like we said here, the first step is discretize the domain. Then the next step, then we go into the next steps. Actually, we reviewed that the next step is discretize the PDE so that you end up with a system of equations like we saw here. And finally, we solve this system of equations. Therefore, the next step is discretize the PDE. And finally, solve the system. Therefore, I start from discretizing the domain. The OpenFOAM class that is used for discretizing a domain is called finite volume mesh. I create a finite volume mesh, noted by fvmesh, and call it mesh. I create this object. This object can be created in many ways. We create it from a mesh file. As you are familiar, any OpenFOAM case has a number of files, including a constant inside which the mesh is saved. So we read the mesh from basically our test case. And what is the mesh file? We know that the mesh file, so we should tell it what the mesh file is. Mesh file is an input-output object. Basically, whenever you interact with the disk, you are using an input-output object. So we are going to read the mesh files from the disk. We need an I/O object to do this operation. I/O object mesh file by default, the name of the mesh in OpenFOAM is region 0. It is hard-coded into the polymesh class. And as far as the mesh is just a single region, or like our test case, the name of the mesh is region 0. Yeah, like I said, this name is hard-coded. You should follow this. I think I'm trying to show you what keys I hit so that you get a feeling about how we use Vim also. It might also be useful. So now it is in a better place. So when I hit a key, you see here, and when I click also, you see it here. Where I am actually. I don't know what happened. Yeah, we are inside the draft. I jumped out for some reason. Yeah, so we said that. Okay, what is it? Yeah, we were here in this tab. Okay, so we are creating a mesh file to interact with the disk, to read the mesh from the disk. We say the name is region 0, hard-coded in the OpenFOAM. And then which directory this is going to be read from, like we know, mesh is already in the constant directory. So we say runtime constant. And well, we have yet to tell OpenFOAM what do we mean by runtime. We will say that soon. Then go read region 0 from runtime. And yeah, we should tell it that you actually need to read this IO object by a so-called IO object enumeration. So this operator is called a scope operator. The name that comes after belongs to the IO object class. And we say must read. And finally, IO. Yeah, that's it. So we are saying that go read region 0 from constant. Yeah, do read it, must read. And then we create from this mesh file, we create our mesh. We basically read our mesh into an FVMesh object. One more thing here is object registry. It is OpenFOAM's designed that you need to register, you can register objects. Sometimes you have to, sometimes it is optional. For the mesh, you have to, for this mesh, you have to, for the mesh object, you need to register the mesh with time. It is OpenFOAM design. Actually, you do not have any other object as far as our code. We do not have any. Of course, we have yet to create time also, but when we create it, the only object that is created before mesh is time. So we register our mesh with time. And we will talk about object registry a little bit later, what it is for mainly. So as far as I know, I have created the mesh file and here we go. This is our mesh. Then I discretize the PDE. If I go to the slides, we discretize the PDE. The way we do this is, so yeah, we end up with, it is just an example of a wave equation as we did for the heat equation. Yeah, we can discretize the wave equation also. So the way the OpenFOAM notation for the wave equation looks like this. You discretize the time derivative term and you discretize the Laplacian term, and this is the notation you go ahead with. So I will write this notation, but before that, you should know that this system of equations itself is an object, and this object is, as you might guess, it is finite volume matrix. So a matrix that is generated by finite volume procedure. Finite volume matrix. And since the quantity is a scalar, we use this syntax as to scalar. What we are going to solve for is u, and what is u? U is the amplitude of the wave. So the amplitude of the wave is a scalar. Then FE matrix scalar is generated using the syntax that I just showed you. FV m d2 dt2, the second derivative of time, the second time derivative of u equals FVM Laplacian, some constant, we can call it C2, like we have it here, C2, and U. So here we go. And finally, the object-oriented programming gives us this, actually enables us to easily solve this equation by, well, we need to name this object, FV matrix scalar, U equation, and then finally, U equation dot solve. So now we get back from the top, we review our code. Here we say int main at the very top. As you know, there exists, so just give me, let me give you an idea about what's going on in terms of the agenda. We will continue until, I think, another 30 minutes until we are done with writing this solver and we see the results. And then I will give you a small quiz, and you will have another 25 around-ish minutes to complete the quiz. And then if you have any questions and any thing you want to talk about, we can talk afterwards. In the meantime, we will fill out a very quick feedback form also. So as you know, there exists a standard authority called ISO. ISO standard committees prepare standards for everything, including for C++ coding. So C++ has its own standard committee, and ISO has its C++ has its own ISO standard committee, and ISO C++ mandates you to have only two types of main function. Your main function might look like this. It returns integer and it gets no arguments. Or the second alternative is it gets two arguments. The first one is an integer, is the number of arguments, arg count, and the second one is the arguments themselves, which are character star arg v. So ISO C++. We do not get into this kind of strange syntax, why it is the case. Just for now, accept that this is the ISO convention for writing the main function, either this one or the one above. But most of the large code bases, including OpenFOAM, use this alternative because they need to get arguments from the user. For example, when you go for simple foam, so let me activate OpenFOAM 12, which we use. When I go for simple, let me see if my performance is active. Yeah, it makes everything smoother. Simple foam, everything that you specify by a hyphen and then the word is the arguments. We are talking about arguments. So these are the things that get passed to the main function. Therefore, OpenFOAM uses let me see, which one was it? Jobs. Yeah, we were here. Therefore, OpenFOAM passes arguments, and when actually you pass arguments to the application, then OpenFOAM needs to parse the arguments. For example, we saw the simple foam has an option called parallel. So it needs to pass that inside the solver, and the object that does parsing for us, parse args, is an arglist object. Arglist object gets argc and argv that we had here, that is given by the user. So when we have the user might or might not pass any arguments, but in any case, we need an arglist object. Then using the arglist object, we can create a time object. Why do we need to create a time? Because as you saw, we need time to create the mesh IO object and then to create the mesh itself. And also, we will see that we need that to loop over our equation. We want to solve this U equation for in time, basically. We have a time derivative. We want to solve it for a time-dependent problem. So we need time. We create a time object, call it runtime. And a time object can be created in many ways. The way that we use is using two arguments. The first argument is the name of a file where time controls exist there. The time controls, as you are well aware of, are inside a file called control-dict. We call it banana for now, just for me to show you that the name does not have to be control-dict. And then the arglist object itself, args. So this way we create a time object called runtime. Then the runtime is known, and the runtime that we have used here is already created here. So before I continue, I go back to the first line. I have argList here. Any class that you use to create an object needs to be declared at the top. So things that we used are, maybe I'm not sure if I can go to the full screen. Yeah, okay, we can go to the full screen. It is good. Yeah, I'm at the very top. Yeah, now that I'm in a full screen, you might have a hard time to see that. So let me exit the full screen then. Because this thing at the top covers what I'm writing at the very top. So we need to declare whatever we have used. Here, the first class we have used is argList. Include argList.h. The next thing we use, the next class we use to create an object is time. Include time.h. Then the next thing is IO object class. Include IO object.h. fvmesh and fvmatrix. fvmesh, fvmatrix. What else? Then we have a careful look at whatever terminology that we have introduced into our code, because the compiler or the computer doesn't understand anything unless you tell it. So we said what argList is, what time is, then IO object. Here everything is known. Then word, I know that word itself is in a place where automatically searched by OpenFOAM. We will get to that point soon. So what else? Scalar is a word that we have introduced, and FVM. So I go to the top. Well, also I know that scalar is, just in case I add it, but if I don't, we don't have a problem, because like the word scalar is also at some directory that is automatically searched by the compiler. Then FVM, and anything else after FVM, like I said, this is the scope operator. Anything that is in the scope of operator is known as soon as FVM itself is known, as we made FVM known by this line. So these lines are called include directives. What they do is that when we compile the code, they basically go find this file and copy the content of the file at the top. So having this line here literally means that I go copy the contents of argList.h and paste it here. That's it. This is what these lines do. And a note on the there's one question. We are just saying that go find these files and copy them here, but where are these files? This is something that also we need to tell OpenFOAM. So I will go into my terminal. As far as I know, I have a waveform.c. By the way, we normally write ls. I have created an alias that gives me a bit more information, and I call it lh. So basically, it is doing the same thing as ls and shows just a bit more information. So to compile using OpenFOAM compilation system, we need a directory called make. And inside make, I need two files. The first file is called files. I just create two empty files for now. Touch creates an empty file. So make files and make options. Therefore, this is my directory structure now. I have waveform.c and I have a directory called make. So now the first thing I need to change, I want to go inside the files and edit that to make it suitable for OpenFOAM compilation system. So files is now empty. I'm inside files. I say that then the file that you're going to compile is called waveform.c. Compile it into an executable inside, save that executable inside foam user application binary. Foam user application binary and call it waveform. Therefore, this is directory. Save my application inside this directory. And then we go to make options. We have make options also. Here we answer this question. Where do you look for these files? Some files, as I said, are automatically found by the compiler. Which files? If I look at OpenFOAM source directory, foam source, you see that I have a lot of directories here. Specifically, the one of them is called OpenFOAM. Anything inside OpenFOAM is automatically searched by OpenFOAM's compilation system. So any file that is there is not needed to be addressed. For example, I know that word.h or scalar.h is there. However, anything that starts with FV, we have FV mesh, finite volume mesh, finite volume matrix, finite volume method. Anything starting with FV is inside another directory in foam source called finite volume. So it is outside OpenFOAM. Therefore, we need to tell the compiler where to look for this. And we do that now. The way we do that is that exe include these things into our executable by looking into, by including foam source, finite volume. And then inside finite volume, you have a number of other folders, number of other directories, but all of them are linked. Well, if I show you, there is one directory called ln include. If I show you ln include, you see that inside ln include, you have links to all of the files that exist in the finite volume itself. So any .c or .h file that exists in finite volume is linked into a link in link include. So this is OpenFOAM style for making it easier to find files. Therefore, we just need to go search inside link include instead of going searching every single directory one by one. After doing so this answered this question as to where to look for these files. Then when actually the program wants to get compiled, it also needs an implementation for every single library. These lines are just declarations, as we have covered in the previous session. These are just the declarations that, for example, FV mesh, there exists an FV mesh, and this FV mesh can be created using an IO object as we did in the code. So this is the whole thing that these lines tell us. But how do I actually create a mesh from a file? That is in fvmesh.c, and that is already compiled into the finite volume library. Therefore, we need to link our code with that library. Therefore, these are the declaration for compiling our code, we need our application to be linked to the definitions which exist in the library. Therefore, I say exe libs the libraries, L, which is the short for library, go link my code to finite volume. And well, it is OpenFOAM style to add a backslash here, go to the next line and give 4 space indentation. It is not mandatory, but it is just for increasing the readability. Here we go. So our options is also done. So I have waveform, I edited files, I edited options. Let's go back to waveform. So I answered this question. I have everything here. The next thing I need to do is, I should say, what is the context of our code? The context, or the technical word for it, is the namespace. All of these names, for example, arglist, time, etc., have their own meaning inside the OpenFOAM namespace only. So using namespace foam, we have discussed the concept of the namespace in the previous slides, in the previous session last week. You can go find it in our website. So when using basically foam namespace, all of these lines of codes get some meaning. So we have yet to do a few more things. The only things that we have left to define is the U itself, the field U, and the C2 constant. So I will create U and constant. So create properties. Why do I call it properties? Because C2 is a property of the medium in which the wave is propagating. So I create, so C2 is a dimensioned scalar. Dimensioned scalar. Let's call it C2. And there are, again, a few ways to create a dimension scalar. The way that we use is we give it a name. So the constructor that we use gets 3 arguments: a name, dimension. For dimension compatibility in this equation, on the left-hand side, I have meter over time squared. So on the right side, for me to have the same dimensions, C2 needs to be meter over second, the whole thing squared. So dim length over dim time, the whole thing to the power of 2. The whole thing to the power of 2. And finally, a value. What is the value of this scalar? For example, I say 1 for now. Then I create the field, the U field. Create field. All fields in OpenFOAM are created by a class called the geometric field. Geometric field. And since it is a scalar field, it is a geometric field of scalars. The scalar is the like we saw here, the scalar is the amplitude of the wave. Yeah, we are here, geometric field of scalar. Then the next, we didn't cover we covered templates a bit. You see that I am using a bit strange notation, using this greater than and less than syntaxes. So basically, this whole thing is one name. This whole thing is one name. Don't be confused by this greater than and less than symbols. Anything that comes inside these 2 symbols is called template parameters. And geometric field gets 3 template parameters. the type of the field itself, the type of the boundary, which is FV patch field, and we are going to save our field at the self centers, not at the face centers. So to do that, we use a volumetric mesh. If we were solving for a field over a surface and we were saving our fields at the face centers, it would be surface mesh, and if it would be FVS patch fields, FVS patch field rather than FV patch field. So we create this field, call it U. Like what we did for the mesh, we create this field using a field file and a mesh. So basically, mesh can be generated using mesh file only, but field needs both field file, which is an IO object, and the mesh that corresponds to the field. So what does the field mean? Field is basically a list of values which we correspond to a mesh. We say this is the value of the first cell, this is the value of the fifth cell, this is the value of the 100th cell, and so on. So to make this correspondence, we need to let the field know which mesh it's going to be corresponding to. So we need to create the field file like we did for the mesh file. So the field file is an IO object, Why? Because as definitely all of you have run a single OpenFOAM simulation so far, and you know that there exists a directory called 0 in which you decide about the boundary conditions and the initial conditions. So you read the fields from the disk. This is OpenFOAM design. You read the fields from the disk to start your simulation. So although there are scenarios that you don't have to do that, but this is the most conventional way to do that. To read the fields from the disk means you need to interact with the disk, so you need an IO object. I copied the mesh IO object and just edit that. Okay, what happened here? I think I deleted something. It was really strange. This thing was deleted totally. Why? Okay. I think a few things are deleted here. IO object was deleted. I don't know why. Okay. Field file. It's not a big deal. That happens. My field file is called, it needs a name whose name is U. Then I need to tell OpenFOAM where to look for the file. It is inside the time directories. So runtime name means the time directories. If the control dict says go read from the start time, and the start time is 0, it looks into the folder 0, looks for a file called U inside 0. Then I need to register the field. Again, the OpenFOAM design is normally to register fields with mesh, and we will get into object registry a bit later, soon actually. And finally, we need IO object. We need IO object options. We need to read. We need to tell OpenFOAM, go do read this from the disk. And we also want to write the results. When we solve for U, we want to write the solved U. So that is specified by auto write. Cool. So from the field file and the mesh, I can create the U file. I can create the U object. Now I have U, I have C2, and everything here is declared. So the mesh file is also seems okay. Okay, we are done. Now let's compile. The compilation, as we covered last week, is done easily by wmake when everything is set up. So we get a few errors. The first error is saying that, okay, what is this semicolon? Yeah, obviously this semicolon is not essential. It is, so we already have a semicolon here at the end of the object creation. So the code gets compiled. Now, in order to test it, I'll copy cavity tutorial, foam tutorials. Actually, since we don't have time, I already have a tutorial, but maybe it is not a bad idea. Yeah, I think we don't have. Well, give me 1 second, and I will see where the previous code is. Well, maybe it is in Minifoam. I'm just trying to save time. Okay. Uh, so here we have a simple cavity test case. So I just copied it from the foam tutorials. It has a number of things that we don't need, like uh, turbulence fields, which we don't need. Then I have created okay, yeah, maybe it's not a bad idea if I go back to my own cavity, foam tutorials, fluid, uh, cavity. So so if I run wave foam, it will give me the error as to I cannot find banana. So as you remember, we named our control dict banana. So let's rename our system control dict system banana. And then the next error would be wave foam. It says, so where is where is the mesh? We have not created the mesh. So let's create the mesh. It says, okay, that's interesting. The mesh needs control dict. So let's get a copy of banana, because the mesh does not, it is hard coded in the mesh that it needs control dict. System control dict. So block mesh. Okay, the mesh is created, and I can create a I just want to open my mesh and show you the mesh. We are a bit short of time. I might spend a bit more time on this and give you less time for your quiz, but we are good, I think. So this is our mesh. What we are going to do is I'm going to introduce a disturbance at the middle and see how the wave propagates to every border. So we specify all the boundaries to be zero gradient, which in wave equation means these boundaries are reflecting the wave back. They do not absorb the wave. They do not let the wave go. They just reflect the wave. So to do that, first of all, if I run the waveform again, I need a U field. The U is not created. So I know that I have a scalar field called P. I copy it into U, and then I go to U. Here I have volume scalar field. I rename the object to U, and remember that the dimensions was meter squared over time squared. And then let's say the uniform value is 0 everywhere, and every boundary needs to be zero gradient except front and back. Yeah, front and back is this at the front. If I show you front and back only, yeah, these two are front and back. These are empty. So our problem is 2D. And cool. So I want to introduce a disturbance in the middle. Actually, based on the agenda, it is now the time for us to switch to the quiz. Therefore, in order to not fall behind on the agenda, I show you the next steps from a prepared test case rather than doing it live here. So like I said, I want to introduce a perturbation at the very middle, whereas here inside U, we have the field to be zero at all places. So we need some disturbance at the middle. The way we introduce that disturbance is sorry that I go between too many tabs. I just want to find some test case. So system, inside the system, do I have yeah, I think it's not a big deal. We can easily make that. So actually, yeah, I just want to save time. Let me just find the test case I'm talking about. We can create that disturbance at the middle of the domain using set fields. And if I go to here, do I have set fields? Yes, I do. So okay, set fields. I do the set fields. It says set fields dict. I am a bit okay, gotcha. Sorry. So you need, sorry for too much of a confusion. I just wanted to save time, but actually it made you a bit confused possibly. The plan was that I do this live, but I think it takes me, well, yeah, let's just spend another 5 minutes on this and see where we get actually. Then we switch to the quiz and you will implement your own solver. So don't forget, what we are going to do is this field everywhere is zero and we want to introduce a disturbance in the middle. What we do is that we say foam get set fields dict enter, and it asks you, okay, because OpenFOAM 12 foam get set fields dict. It says, okay, we have two options. Which one do you want? We normally choose the one that is not annotated, which is normally option 2. So I have already done that, and I have that in my system, set fields dict. And in set fields dict, if I show you the bounding box of this mesh, check mesh, grep. So the bounding box is that this mesh is stretched from 0, 0, 0 to 0.1. So this is the diagonal of this mesh. Therefore, if I want something in some small box in the middle, I need to choose a box that encompasses a number of cells in the middle, and I do that in the set fields. So in the set fields, I have said that the U field everywhere is 0, but go choose a box, and this box is just a small box in the middle, and set the U value to be 100. And if I run set fields, we will see that if I reload the file, okay, system, sorry, I need to do a small, I need to change the Z. Well, Z is the direction in which the geometry is empty, so it doesn't matter what that direction is. I say it from a very far minus to very far positive, set fields. And now if I reload the mesh, well, I still don't see that. Why? Set fields U. So possibly I'm looking at the wrong mesh. And for some reason, I can open ParaView only in a new tab when OpenFOAM is activated in my terminal. And this is a well-known bug for the foundation OpenFOAM. Okay. System, block mesh ticked. What is my block mesh here? So first of all, my block mesh was not designed for a 2D case. It was designed for a 3D case. I'll go change that first, and then front and back, let it be empty. And then I create the mesh again and set fields again. So it says, I go to the U. So since I have already run the set fields, the values here are initialized. I delete that. As you remember, the initial value of U was uniform 0, and I set fields again. It says, so for front and back should be empty. We changed it to a 2D case. Set fields. Here we go. So if I reload this and I show the U, you see that I have, using set fields, I introduced that disturbance at the middle. So then the next thing is to run waveform. As you see, waveform solved the equation for one iteration only. And it is not written either. It is still in 0. So I go back to our code. There are two things that we need to do. First of all, instead of reading the code from, actually, instead of hard coding the value of our scalar here, we can read it from a dictionary. The second thing is that we need to include this PDE discretization and PDE solution inside a time loop. And finally, we need to decide how to write the results. So let's have a 5 minutes break. We are actually we still have another 30 minutes. The plan was that we specify this 30 minutes to the quiz, but apparently we actually need to get a chunk of this 30 minutes to complete our code first, and then we get into the quiz, and then you can stay maybe another a few more minutes if you want to. I can also to uh, to actually get where we plan to get for in terms of the quiz. So I'll see you in 5 minutes at 2:35 Dublin time. Okay, guys, we are back and let's continue. I think you have my voice and my video. Cool. I need to share my screen again. Where is my Zoom controls? Well, my Zoom controls disappeared actually. I don't know how to share my screen now. Yeah, here it is. Okay. Okay, so let's continue with the things that we decided to do. The first thing is, so I'm hearing myself. Let me continue. Mute myself. Where is it? Yeah, actually, I had a few things open and I was hearing myself. So yeah, the first thing that we want to do, so let's say if we come to this, yeah, actually, I will come back to this dimensional scalar thing later. For now, we want to solve the equation for many time steps. As far as we basically want to give the solver the start time and the end time, and the solver runs from the start time to the end time. So we put this equation discretization and solution into a time loop. Why do we only do this, put this part into a time loop? Because actually this is the only thing that changes by time. The equation itself is time dependent, so it should be in a time loop. Every time it changes, the system of equation changes. When the system changes, the solution changes also. And the solution is the thing that we are looking for and we are writing this whole code for. Therefore, this whole thing should be inside a time loop. We say while runtime loop. That's it. So runtime loop, what this line does is it looks into the control dict time controls. As long as the end time is not reached, it returns true. When it returns true, the code gets inside the while loop. When it returns false, which means we have reached the end time, the code inside the while does not execute anymore. So I put everything inside the while loop. And one more thing is that we want to take care of writing the results also. We want to see the results, the results that we have solved for. So write the results. In order to comply with time controls in control dict, we first look at the control dict and see if it is the right time or not. To do that, we say if runtime write. So it means if it is the right time by decided by control dict, then write the result. What is the results? The result is the u field, u.write. Now, I promised you that we will talk about the object registry. Here we go. If I had 10 fields instead of just one field, which actually occurs, for example, in the problems that the severe deformation problems that I deal with, sometimes we have as high as 80 fields. Obviously, not all of them are the fields that you solve for. Some of them are secondary fields that are obtained explicitly, but you have many fields and you want to see them in your post process. In that case, I would have had to write field 1.write, field 2.write, field 10.write, field 80.write. I had to write this line 80 times if I had 80 fields. The idea of the object registry is that you do not have to write 80 lines. Rather, tell me which object your fields are registered with and just write the object registry. We know that the fields are registered with the mesh we decided here. The field U is registered with the mesh. Therefore, just write the object registry. So whether you have only one field or whether you have 100 fields, mesh.write writes everything. everything that is registered with the mesh, as well as the mesh itself if the mesh has changed. In our case, the mesh is static and the mesh is not written in the time directories. Then when writing is done, we say, well, just print end. Go to the new line. Okay. I compile it. I'll go to my okay, the compilation was successful. So if I run waveform now, so it executes for quite a few, for all the times. If I go to banana, which is my control dict basically, I have decided that start from 0, go to 1, and the delta t is 0.01, and write interval. So it writes all the time steps basically, because the delta t and the write interval are the same. And if I look at it here, I see that all the time steps are written. So I reload the files and play the animation. Okay, you can see that the wave gets propagated very well again. Okay. To show actually that wave shape, I wrap this domain by amplitude itself. So what we do is, first of all, the fields, the visualization that you see is based on the values at the cell centers. The values are saved at the cell centers. In order to use the filter that I want to use, I need to interpolate the values to the points, to where the edges cross each other. And to do that, there is a small option here, create cell to point filter data. If you are using another version of ParaView, you can find it in the filters called cell data to point data. So I create that interpolation, then I can use warp by scalar. I warp by my domain by the magnitude of the perturbation. So the magnitude of the perturbation is very high, so that you can see it goes to very, very high altitudes. So I just multiply it by a small factor so that it falls into our scene even smaller. So here we go. This is our perturbation in the center. If I color this with hue, so you can see that the perturbation in the middle is going to propagate in the domain. So here we go. So you can see that the wave is propagating very fast. The wave is propagating very fast. What I will do is, instead of hard coding the material property, I read it from a dictionary. So I have C2, whose name is C2, fine. And this dimension is this, and then the value, I do not hard code the value. I read it from a dictionary, but let's first create a dictionary. Again, the dictionary is a file, and this file is going to be read. So I create an IO dictionary, and I call it waves properties. It is also going to be, so for in case of the mesh and field, we first created the IO object outside, and then we included in the constructor here. But here for this dictionary, I just do everything inside the constructor. I do not create the file name outside, the file object outside. By the way, IO object is not always a file. It can be many other things. But for now, in the scope of our program, an IO object coincides with a file. So wave properties, again, needs a name, word, I call it wave. So first of all, it is an IO object. And the IO object needs a name, wave, properties. Just to give you an idea, we have around 10 minutes left. So our quiz might become an optional thing then. So it is, by the way, optional. We just might not have time to interact on the quiz. I just let you know what the quiz is, and then you can go ahead on your own. So then read the waves properties from the constant, runtime, constant, runtime constant, then register that with the mesh, and I just copy this. We want to write it, so we should create the IO object in a way that it forces reading from the disk, and then we do not want to. We want to read it from the disk, so must read, but we don't want to write it because it is just some properties that we read, and then we don't have anything to do with that afterwards. So from the IO object, the wave properties is created. Then here, instead of saying one, I say go read it from the dictionary. So I say wave properties look up a scalar whose name is C2. So what this line means, first of all, wave properties is an IO dictionary object. IO dictionary object is itself a dictionary object. So the dictionary is the parent of IO dictionary. And all dictionary, the dictionary class has this member function lookup, which looks up a file and finds the keyword and the value corresponding to the keyword. So we say go to the wave properties, find the C2 keyword, and read its value. The C2 is the key. What is the value of the C2? Read that into this place. So we already had one here. So read this, the output of this into this place to initialize C2. Let me compile it first. I think I had a spelling error. Wave properties. Oh, okay, it was waves here. So let it be wave properties. Okay, it gets compiled. And now I go to my constant and create a, so let's delete the existing wave properties, rm constant, because I have already ran this case using another solver. So constant wave properties, it is an empty file. All OpenFOAM dictionaries need a header starting like this, foam file. It needs 3 entries. Format is ASCII in our case, which is human readable, which means the format is human readable. Then the object is wave properties, and then class, it is a dictionary. And then we said that go look for the keyword C2, and we already decided that, so C2 was hard-coded to be 1. Now I say it is 1e-3. So basically we created a dictionary called wave properties, and we respected OpenFOAM notation for dictionaries. OpenFOAM syntax for dictionaries. Okay. So I want to rerun my case. Therefore, I say foam list times, list all the times and remove them. Then waveform again. So now I reload the case. If I go back, I reload the case. And now you can see that the wave is propagating much, much slower because we changed the medium, the properties of the medium. Actually, you can run this test case in 3D also, but since we don't have time, maybe I can show you in the website. So first of all, this is C++ for OpenFOAM from zero, the past event that you can go and find the material for that session if you missed it. Then let me see. Well, I don't think I have maybe it is in the products. Yeah, here. Yeah, in 3D, you will have things like this. So the wave propagates in 3 dimensions, in 3D. Well, it is a matter of visualization techniques in the preview. For example, here I have used ISO surfaces. Here I have used threshold. So you have ISO surfaces here, and you have threshold here. You can experiment with them using a 3D case and generate figures like this. So we are done. We are left with only 5 to 6 minutes to the end of the session. And we actually, the next thing that you were meant to do were to implement the heat equation. Very simple. We implemented the wave equation. You go implement the heat equation and solve it. Let's use this remaining 4 minutes for filling out the feedback form first, and then yeah, you can actually I will give you the links for accessing the material, and then you can follow this on your own. In case you have problems, you can always book a call, whether you have problem in this homework or you have problem on your specific projects. We have, well, appointments for free that you can book. Yeah, that's it. Let me share the feedback form with you. I think I have it somewhere. Let me stop sharing here and just send the link to you. If you don't mind, please fill out the feedback form. I will put it in the comments of LinkedIn live and YouTube live also. I just want to yeah, here we go. I now put it in the chat. Where is it? Okay. Okay. The link is not copied. Copy link. So now the link is in the chat. So if you don't mind, please spend the remaining 3 minutes. It would take you less than 3 minutes. Please fill out the form. Meanwhile, if you have any feedback, verbal feedback, or any questions, feel free to turn on your mic and have a chat. Okay, I think we are done. I hope you had the chance. First of all, I hope you enjoyed and it was useful for you. And if you didn't get a chance to fill out the form, please do as soon as you can. Give us a feedback. And yeah, you can have access to the previous material from the website. I will send you a follow-up on how to access the material for this course. And feel free to reach out if you have any questions for your own projects. Have a good day and bye-bye.